Right now, at this very moment, the fastest object humanity has ever built is hurtling through the void at approximately 4,300,000 miles per hour. That number deserves a moment of silence. 4,300,000 miles per hour. Roughly 119 miles every single second. Faster than any bullet, faster than any explosion, faster than anything manufactured by human hands has ever traveled in the entire history of our species. The Parker Solar Probe, a spacecraft the size of a small car, achieves this velocity during its closest approaches to the Sun, using the star's own gravitational field as a slingshot, accelerating to speeds that would carry it from New York to Los Angeles in less than a tenth of a second. And if you pointed that spacecraft directly at the nearest star beyond our Sun and asked how long the journey would take, the answer would stop you cold. 6,800 years. Not 6,800 days, not 6,800 months, 6,800 years. You would depart Earth before the invention of writing, before the first city was built in the Tigris-Euphrates Valley, before the Bronze Age began, before any dynasty in any civilization had risen or fallen. You would arrive after a duration that encompasses the entire recorded history of human civilization. Every war, every empire, every scientific revolution, every cultural transformation that separates a Mesopotamian farmer from a physicist working in Geneva. And then you would need to repeat that span again and then again, totaling a journey so vast that no human framework of reference can honestly contain it. And Alpha Centauri, the destination in that calculation, is the closest star to us. It sits practically on our doorstep in galactic terms. But here is what most people do not fully grasp when they imagine interstellar travel. The problem is not simply the distance. The problem is that the distance cannot be shortened, not through cleverness, not through engineering, not through the kind of patient technological progress that carried us from the Wright Flyer to the Saturn V in 66 years. The speed of light is not a record waiting to be broken. It is a wall, woven into the structure of space-time itself, confirmed by over a century of experimental evidence ranging from the decay rates of muons in particle accelerators to the behavior of atomic clocks aboard GPS satellites. Nothing carrying mass can reach it. Nothing can exceed it. Every film you have ever seen that depicted a starship casually jumping to warp speed was depicting physics that does not exist in this universe. Warp drives require exotic matter with negative energy density, a substance that has never been observed. Wormholes require stabilization mechanisms that violate known energy conditions. These are not technologies awaiting development. They are mathematical notations on paper that have never made contact with physical reality. This means that if humanity ever travels to another star, it will travel slowly, agonizingly, devastatingly slowly. If you enjoy explorations of real science that do not flinch from uncomfortable conclusions, content that takes the universe seriously and asks what it actually permits rather than what we wish it would allow, I would genuinely appreciate it if you hit that like button and subscribe. It helps this channel reach people who are looking for exactly this kind of depth. Now settle in and get yourself comfortable. The journey we are about to take is a long one, and what waits at the end of it will change how you think about the distance between the stars. Let's begin. A generation ship is not a spacecraft in any conventional sense of the word. It is not a vessel designed to carry a crew from departure to destination. It is something far more unsettling. It is a world, a fully enclosed, self-sustaining habitat designed to carry a human population across the void between stars over a journey lasting not years or decades but centuries, potentially millennia. The people who board such a vessel at departure would never live to see the destination. Their children would not arrive. Their grandchildren might not. The individuals who eventually step onto the surface of a planet orbiting a distant star would be the remote descendants of the original crew, separated from the founders by generations of births and deaths, entirely within the walls of a sealed metal container, hurtling through absolute darkness. Those arrival generation passengers would know Earth only as a word in a history archive, a concept, a mythology. The sky they grew up under would be a ceiling. The ground beneath their feet would be a floor bolted to a superstructure moving through a vacuum, so complete that sound itself cannot propagate through it. They would have been born into confinement, lived their entire lives in confinement, and would die in confinement, passing the mission on to children who would do the same. The generation ship concept exists not because anyone found it appealing, it exists because the physics of distance left no other option. To understand why, you need to feel the scale of what interstellar space actually means. Not just intellectually accept the numbers, but genuinely feel them in the way that makes the chest tighten. The nearest star system to our Sun is Alpha Centauri, a triple star system approximately 4.37 light-years from Earth. A light-year is the distance light travels in 1 year, moving at 186,000 miles per second. 1 light-year equals roughly 5.88 trillion miles. Alpha Centauri sits approximately 25.6 trillion miles away. If you drove a car at highway speed without stopping, the journey would take longer than the current age of the universe. If you built a scale model of the solar system, where the Sun was the size of a grapefruit, roughly 4 inches in diameter, Earth would be a small pebble approximately 75 feet away. On that same scale, Alpha Centauri would be located in another city, not across town. Another city roughly 4,000 miles from your grapefruit sun, and Alpha Centauri is the closest. Tau Ceti, a star similar to our Sun with confirmed planetary candidates that has drawn significant scientific attention, sits approximately 11.9 light-years from Earth. At Parker Solar Probe speeds, the journey requires roughly 190,000 years. The TRAPPIST, one system which generated extraordinary scientific excitement when astronomers confirmed it, contains 7 rocky planets, 3 of them positioned within the star's habitable zone, where liquid water could theoretically exist on a surface, lies approximately 39.5 light-years away. Reaching TRAPPIST, one at our current best speed, would require approximately 63,000 years. That is a span roughly equal to the entire time anatomically modern Homo sapiens has existed as a species compressed into a single, unbroken voyage aboard a single vessel. These numbers are not exaggerations. They are calculations derived from measured distances and demonstrated velocities. They are the foundation on which every generation ship proposal must be built, and they are merciless. The most promising propulsion concepts that operate on confirmed physics, rather than speculative breakthroughs, could, under optimistic assumptions, achieve somewhere between 1 and 5% of the speed of light. Nuclear pulse propulsion, the concept studied under Project Orion, beginning in 1958, which proposed detonating nuclear explosives behind a massive pusher plate, was estimated by physicist Freeman Dyson and his colleagues to potentially achieve velocities of 3 to 5% of light speed. More optimistic fusion variants suggested perhaps 10%. At 5% of light speed, the journey to Alpha Centauri contracts to approximately 87 years, a single extended lifetime. The mission begins to look almost conceivable for the nearest target. But extend the calculation to TRAPPIST, 1, and even at 5% of light speed, the journey requires approximately 790 years, 16 generations, more than the span separating the year of the First Crusade from the present day. At 1% of light speed, a more sober, more grounded projection for near-future capability, Alpha Centauri requires 437 years. Tau Ceti requires roughly 1190 years. TRAPPIST, 1 demands nearly 4,000 years. These are not merely long journeys. They are journeys measured in the rise and fall of entire civilizations. And here is the detail that most casual discussions of generation ships pass over without pausing to absorb. No human-built structure has ever been required to function continuously for even 500 years. The oldest surviving buildings on Earth, ancient stone temples, the pyramids of Giza, Roman concrete harbor structures, are passive monuments. They have no moving parts. They require no power generation, no atmospheric regulation, no water recycling, no biological life support. They sit on the surface of a geologically stable planet, breathing an atmosphere maintained by a global biosphere and warmed by a star located at precisely the right distance. Their survival across millennia is a testament to the durability of stone under benign and static conditions. It says nothing, absolutely nothing, about the durability of complex, active, interdependent machinery under the conditions of interstellar space. A generation ship must perform the exact opposite of passive endurance. It must actively sustain interlocking systems of machinery, ecology, and human society every second of every day for longer than most civilizations in recorded history have persisted. Ancient Egypt endured for approximately 3,000 years. The dynastic history of Imperial China spans a comparable arc. A generation ship traveling to Trappist, 1 at 1% of light speed, would need to function reliably for longer than either of those civilizations existed, and it would do so with no access to the planetary resources, geographic diversity, agricultural land, and population reserves that allowed those civilizations to absorb catastrophes and rebuild. A generation ship that suffers a civilization-level collapse has no territory to retreat to, no neighboring kingdom to absorb refugees, no ocean to cross in search of better conditions. There is only the sealed metal interior and the void pressing against every surface from outside. This is the premise. This is the ground on which everything else rests. Engineers who have studied this problem seriously, not science fiction writers but aerospace engineers, materials, scientists, ecologists, geneticists, and sociologists, working from peer-reviewed literature, have arrived at conclusions that the genre rarely acknowledges. The barriers to a successful generation ship mission are not dramatic. They are not the stuff of exciting cinematic moments. There are no alien encounters in this analysis, no rogue AI systems turning against the crew, no catastrophic explosions in the engine room. The barriers are quiet. They are slow. They are invisible at any individual moment but inexorable across centuries. They are the sound of a metal bearing slowly grinding against its race in a ventilation motor that has cycled 10 million times. The sight of a polymer seal imperceptibly flattening under compression over decades until it no longer holds. The silent migration of displaced atoms through an irradiated crystal lattice, making a structural member slightly more brittle this year than it was last year, and slightly more brittle next year than it is now. And the gradual generational erosion of the technical knowledge needed to recognize and repair these failures before they cascade into something that cannot be stopped. None of these processes makes for compelling drama. All of them together, interacting and compounding across centuries, form a barrier between the stars that is just as absolute as the distance itself and far more intimate. The question this video asks is precise. Given everything physics, materials, science, ecology, genetics, and sociology actually know not what we hope, not what we imagine, but what the evidence supports, is a generation ship mission viable? Across what timescales, under what conditions, and where exactly does the mathematics of survival become the mathematics of something else entirely? The answer begins not in the stars but in the metal, in every rivet, every seal, every bearing, every polymer gasket, every electronic component aboard the vessel on the day it departs, because from that moment forward, every one of those components begins a process that nothing aboard can reverse. And it began before the ship even cleared the orbit of Neptune. Every manufactured substance has a lifespan. This is not a design flaw. It is not a failure of engineering ambition or material science expertise. It is a consequence of the second law of thermodynamics operating at the molecular level, patient and absolute, advancing without interruption from the moment any ordered structure comes into existence. Ordered atomic arrangements move toward disordered ones. Chemical bonds break. Crystal structures shift. Entropy increases always, everywhere, without exception, and it never reverses itself spontaneously. Not once, not under any conditions, not in any material ever studied in any laboratory on Earth. On Earth, we manage this reality through a strategy so pervasive it has become functionally invisible to daily life. We replace things. When a water main corrodes through beneath a city street, a municipal crew arrives with equipment, excavates the failed section, and installs a new pipe manufactured from raw materials extracted from mines, processed in smelters, and delivered by a transportation network spanning thousands of miles. When a turbine blade in a commercial jet engine develops fatigue cracks, after its rated number of flight cycles, a maintenance crew removes it and installs a replacement produced by a specialized foundry using single crystal casting, techniques refined over decades of metallurgical research. The entire edifice of modern technological civilization rests on one assumption, so fundamental it almost never requires articulation, that degraded components can be exchanged for new ones drawn from a functionally unlimited reservoir of raw materials, manufacturing infrastructure, and accumulated expertise. A generation ship carries no such reservoir. It departs with a finite inventory of materials. That inventory represents the total material endowment for the remainder of the voyage. There are no additional shipments. There is no emergency resupply. There is no rescue mission. Every kilogram of steel, every gram of silicon, every milligram of rare earth, element loaded aboard at departure, is every kilogram, every gram, every milligram that will ever be available until arrival or until the mission ends, whichever comes first. This closed material budget transforms every engineering problem from a question of capability into a question of duration. Humanity knows how to build machines that function. The question a generation ship poses is different, and it has never been answered. Can we build machines that function for 1,000 years without external resupply? The structural skeleton of the vessel is the first place this question becomes physical. A generation ship's hull and internal framework must bear mechanical loads continuously for the entire mission duration. If the vessel rotates to generate artificial gravity through centripetal acceleration, the most commonly proposed method for avoiding the devastating physiological effects of prolonged weightlessness, which include bone density, loss of roughly 1 to 2% per month, muscle atrophy, cardiovascular deconditioning, and progressive vision impairment from fluid shifts toward the brain, then structural members experience cyclical loading with every revolution. A habitat module rotating once per minute to produce approximately 1 standard gravity at its rim subjects its structural elements to a complete stress cycle every 60 seconds. That equals 1440 cycles per day, 525600 cycles per year. Over a single century, 52.56 million cycles. Over 5 centuries, 262.8 million. Over a millennium, 525.6 million stress cycles on every load-bearing member in the rotating structure. Metal fatigue under cyclical loading is among the most exhaustively studied failure modes in materials science. The phenomenon was first clearly identified in the 19th century after a series of catastrophic railway axle failures that killed hundreds of passengers, and it has been responsible for some of the most infamous structural disasters engineering history, from the de Havilland Comet aircraft, fuselage disintegrations of the 1950s, where pressurization cycles propagated cracks at the corners of square windows until the hull ruptured at altitude, to the Aloha Airlines incident of 1988, where accumulated fatigue cracks caused an entire section of the upper fuselage to tear away in flight. The mechanism is well understood. Microscopic cracks initiate at stress concentration points, grain boundaries, surface imperfections, or inclusion sites within the metal. Each stress cycle advances the crack front by a tiny increment. The crack grows invisibly for millions of cycles until it reaches a critical length at which the remaining cross-section can no longer support the applied load. At that point, the component fractures, often with catastrophic speed and almost no warning. Modern aerospace engineering manages fatigue through inspection-based maintenance programs. Aircraft structures are designed with specific fatigue lives, typically measured in tens of thousands of pressurization cycles, and components are inspected at scheduled intervals using ultrasonic testing, eddy current methods, or radiographic imaging. When cracks are detected, components are replaced. This system functions because the replacement components exist, produced by a manufacturing base with access to raw materials and specialized fabrication equipment. Aboard a generation ship, inspection remains possible. Replacement becomes progressively impossible. A cracked structural beam in year 50 might be replaced from stockpiled reserves. A cracked beam in year 300 might require scavenging material from a less critical structure, accepting a permanent reduction in some other capability to preserve a more essential one. A cracked beam in year 800 might have no replacement available at all, forcing the crew to accept a weakened structure, abandon an entire habitat section, or attempt to repair using fabricated substitutes that fall short of the original material specification. Radiation damage to structural materials compounds the fatigue problem through an entirely separate degradation pathway operating simultaneously. In interstellar space beyond the protective cocoon of any star's magnetic field, the vessel is continuously bombarded by galactic cosmic rays. These are not the relatively benign charged particles that constitute most solar wind. Galactic cosmic rays include protons, helium nuclei, and heavier ions up to and including iron nuclei, traveling at substantial fractions of the speed of light, accelerated to enormous energies by supernova shock waves and other astrophysical processes distributed across the galaxy. The most energetic among them carry kinetic energies that exceed anything achievable in terrestrial particle accelerators by orders of magnitude. When a high-energy cosmic ray strikes an atom in a metal lattice, it displaces that atom from its equilibrium position, creating what physicists call a Frenkel pair, a vacancy where the atom was, and an interstitial site where it landed, displaced. A single high-energy heavy ion can initiate a cascade of displacements, knocking atoms into neighboring atoms in a chain reaction that produces clusters of defects throughout the local crystal structure. Over time, these displacement defects accumulate. They migrate through the lattice and aggregate into larger structures. Voids, dislocation loops, precipitate clusters that alter the material's mechanical properties in ways that cannot be reversed by any process available aboard a generation ship. The macroscopic consequence is called radiation embrittlement. The material becomes harder, meaning it resists initial deformation more strongly, but simultaneously becomes less tough, meaning it fractures more readily once deformation begins. Ductile materials that could originally bend and flex under unexpected load become brittle materials that crack and shatter without warning. This transformation has been extensively studied in nuclear reactor pressure vessels, where neutron bombardment produces analogous displacement damage over operational lifetimes of 40 to 60 years. The galactic cosmic ray environment in interstellar space delivers an unshielded dose rate of approximately 300 to 400 millisieverts per year to material surfaces, figures confirmed by instruments aboard spacecraft operating beyond Earth's magnetosphere. Over a century, the cumulative absorbed dose in structural components approaches 40 sieverts. Over a millennium, 400 sieverts. The embrittlement that begins to manifest measurably in reactor steels after decades of neutron exposure would be deeply advanced in any unshielded structural member after centuries of cosmic ray bombardment. The critical interaction between fatigue and radiation damage deserves particular attention because the two processes do not merely add to each other, they multiply. Radiation embrittlement makes materials more susceptible to fatigue crack propagation. Fatigue cracks create stress concentrations that make radiation-damaged zones more likely to fracture catastrophically. A structural member experiencing simultaneous cyclical loading and continuous radiation exposure degrades faster than either process alone would predict. The combined effect is synergistic, and it has been confirmed in irradiated steel specimens subjected to fatigue testing in laboratory conditions. The hull does not choose which problem to face first. It faces both always at the same time every second of the voyage. Micrometeorite bombardment adds a third degradation pathway. Interstellar space contains dust grains, remnants of stellar outflows, supernova, ejecta, and cometary debris distributed thinly throughout the galactic disk. A vessel traveling at 3% of light speed encounters these particles at relative velocities exceeding 9,000 kilometers per second. At such speeds, a dust grain massing 1 microgram carries kinetic energy sufficient to excavate a small crater in metal. A grain massing 1 milligram impacts with roughly the energy of a rifle bullet. Over decades and centuries of sustained bombardment, the outer hull surface develops a progressively roughened texture, pockmarked with impact craters of varying size. Each crater is a stress concentration point. Each stress concentration point is a preferred site for fatigue crack initiation. The surface becomes slowly and steadily more compromised than it was the day it launched. Now consider the power systems, because without continuous electrical power, none of the other problems matter. Atmospheric processing halts, temperature regulation ceases, water recycling stops, food production lighting extinguishes. Computational systems managing every other operation go dark. Power is not one critical system among many. It is the prerequisite for every other critical system simultaneously, and without exception, every second of the voyage. Nuclear fission is the most technologically mature option for deep space power generation. Fission reactors have operated in space, notably aboard Soviet Rorsat and Topaz satellites, and modern compact designs, such as NASA's Kilopower project, which successfully demonstrated a prototype in 2018, show that small reactors using uranium-235 fuel can function reliably in space environments. The physics is proven, but terrestrial fission reactors, operating under far more benign conditions, with regular maintenance and component replacement, have operational lifetimes of 40 to 60 years. Beyond that threshold, neutron irradiation has embrittled the reactor pressure vessel to the point where continued operation poses unacceptable fracture risk. Fuel cladding has degraded. Control rod mechanisms have worn. The reactor has not exploded. It has simply aged beyond the point where its integrity can be guaranteed. A generation ship cannot replace its reactor pressure vessel. It cannot manufacture fresh zirconium alloy fuel cladding. It cannot rebuild control systems using components fabricated in a state-of-the-art semiconductor foundry. Whatever the reactor consists of at departure must be what it consists of for the duration of its operational life, and that duration must span not 60 years but potentially 10 times 60. Radioisotope thermoelectric generators, the technology sustaining Voyager 1 across 47 years of operation, offer extraordinary reliability through the complete absence of moving parts. But their power output decays with the half-life of the fuel isotope. Plutonium-238, the standard RTG fuel, has a half-life of 87.7 years. After one half-life, output drops to 50%. After two half-lives, 25%. After three, 12.5%. An RTG-powered generation ship would face a steadily diminishing power budget that would force progressive shutdown of non-essential systems over the course of centuries. A slow strangulation by radioactive decay curves that no engineering intervention can alter, because the decay rate is written into nuclear physics, not into any design choice a human engineer could revise. This brings us to the problem that quietly underlies every other problem aboard: the manufacturing bottleneck. Modern technological civilization depends on supply chains of extraordinary depth and specialization. A single integrated circuit, the kind found in any household appliance, requires photolithographic equipment costing billions of dollars, ultra-pure silicon refined through dozens of chemical processing steps, photoresist chemicals, synthesized from petroleum precursors, dopant gases of extreme purity, and cleanroom environments maintained at particle counts below 10 per cubic meter. The knowledge required to operate this process is held by specialists who train for years in institutions supported by research universities, national laboratories, and corporate research divisions representing centuries of accumulated expertise. A generation ship cannot carry a complete semiconductor fabrication facility. The mass volume, power consumption, and chemical feedstock requirements are prohibitive. It could carry stockpiles of replacement electronics sufficient for some period of time, but those stockpiles are finite. When the last spare processor fails and no replacement can be manufactured aboard, the computational capability it provided is permanently gone, not temporarily unavailable. Gone. And every system that depended on that processor degrades accordingly. The manufacturing chain is recursive in a way that makes the problem self-amplifying. Precision machining requires machine tools. machine tools require cutting inserts made from tungsten carbide or ceramic materials. Those inserts wear out and must be replaced. Replacement requires either stockpiled spares or the ability to manufacture new inserts from raw tungsten and carbon feedstocks using powder metallurgy techniques. Powder metallurgy requires furnaces, presses, and mold equipment, each with its own maintenance demands and material requirements. Every tool needed to make a component requires other tools to make it. Those tools require still other tools. On Earth, this recursion terminates at the mining and refining industries, which extract raw materials from geological formations using energy from combustion or nuclear sources. Aboard a generation ship, the recursion terminates at whatever raw material stockpiles were loaded at departure. When those stockpiles are exhausted, the chain breaks at its foundation. What makes this so insidious is that the regression does not announce itself as a single dramatic crisis. It manifests as a slow, stepped descent through plateaus of diminishing capability, each step appearing manageable in isolation, each step permanently foreclosing options that previous generations took for granted. In the first century, electronic stockpiles deplete. Processors, sensors, and control boards that fail can no longer be replaced with factory-quality equivalents. The crew adapts by cannibalizing non-critical systems, stripping components from entertainment terminals to replace failed units in atmospheric monitoring, computational capacity contracts. Systems that once operated under automated oversight shift to manual monitoring, demanding more crew hours for the same level of safety coverage. The ship still functions, but it functions differently than it did. In the second century, precision machining capability degrades. The cutting inserts for the ship's lathes and milling machines have worn through their stockpiles. Replacement inserts fabricated from recycled materials lack the hardness and dimensional precision of the originals. The tolerances achievable in the machine shop widen. Pump impellers run slightly off balance. Valve seats do not seal as tightly. Pipe joints weep where they once held firm. None of these imprecisions is individually catastrophic. Each one incrementally increases the failure rate of the systems those components serve, and each one is permanent. In the 3rd century, chemical feedstock reserves thin. Lubricants can no longer be synthesized to original specifications because the precursor chemicals are exhausted. Substitute lubricants formulated from available organic stocks perform adequately at room temperature, but break down faster under elevated temperatures inside reactor cooling loops and turbine housings. Bearing wear accelerates. Maintenance intervals shorten. The crew works harder to achieve less. Each generation lives on the plateau it inherits. The engineers of the 3rd century do not mourn the precision machining of the 1st century because they never experienced it. They work competently within the constraints they inherited, unaware that those constraints are tighter than the constraints their grandparents faced. The regression is invisible from the inside, visible only across the full arc of centuries from an outside vantage point that no one aboard occupies. The ship does not fail. It forgets what it was once capable of. One manufacturing process at a time, one materials specification at a time, one tolerance threshold at a time, until finally the gap between what its systems require and what its workshops can provide becomes unbridgeable. 3-dimensional printing and additive manufacturing technologies offer genuine partial mitigation, a versatile fabrication system capable of producing components from recycled metal feedstocks could extend the maintenance window significantly. But additive manufacturing has real limitations. Printed metal components typically exhibit inferior fatigue properties compared to forged equivalents due to residual porosity and anisotropic microstructures. The range of materials printable by any single system is restricted, and the printing equipment itself degrades laser sources, dim build platforms where powder handling mechanisms, clog control, electronics, drift requiring maintenance and eventual replacement from the same finite material reserves it was meant to extend. The overarching pattern is recursive degradation. Systems degrade. The systems that repair degraded systems also degrade. The systems that maintain the repair systems degrade as well. Each layer of this maintenance hierarchy draws from the same finite material and energy budget. Over centuries, the budget shrinks, While the maintenance demands grow, redundancy, the standard engineering response to reliability requirements, provides a buffer. Triple redundancy means 3 independent copies of a critical system. If one fails, 2 remain. If a second fails, 1 remains. But over centuries of continuous operation, redundancy is gradually spent. A system that began with triple redundancy in year 1 might have double redundancy by year 100, single redundancy by year 300, and no redundancy by year 500. At that point, the next failure of that system is the last. The engineering challenge of a generation ship is not building a vessel that works on the day it launches. Human engineers are magnificently skilled at that. The challenge is building a vessel that still works on the day it arrives, centuries or millennia later, after every material has been irradiated, every mechanism has cycled hundreds of millions of times, every seal has compressed, every lubricant has decomposed, and every spare part has been consumed. This is a challenge that no engineering tradition in human history has ever faced. And the physics of material degradation offers no reason to believe that any design, however brilliant, can indefinitely outrun the second law of thermodynamics inside a closed system with finite resources. But entropy does not confine itself to metal and circuitry. The living systems inside the hull, the ecosystems, the water, the air, the crops that must feed every generation from departure to arrival face the same merciless timeline. And they carry vulnerabilities that no amount of metallurgical ingenuity can address. Because the failures that wait inside a sealed biosphere are not written in the language of stress cycles and crystal lattices. They are written in the language of oxygen molecules and soil bacteria, and the invisible competition between a mold spore and a wheat root in an enclosed agricultural bed that has not seen sunlight from a real star in 300 years. What happened in Arizona in 1991 made this devastatingly clear, and the lesson it delivered was one that every generation ship advocate must confront without flinching. In the autumn of 1991, 8 researchers walked into a sealed glass structure in the Oracle Desert of Arizona and closed the door behind them. They did not plan to open it again for 2 years. Biosphere 2 was the most ambitious closed ecosystem experiment ever attempted on Earth. Spanning 3.14 acres beneath an intricate lattice of glass and white steel, it contained a miniature ocean complete with a coral reef, a tropical rainforest, a fog desert, a savanna grassland, a mangrove, wetland, and an intensive agricultural zone designed to feed its 8 inhabitants entirely from within its own boundaries. The designers had spent approximately $150 million and nearly a decade engineering a system intended to recycle its own atmosphere, water, and nutrients indefinitely, a self-contained world within a world sealed against any material exchange with the outside environment. The project was meant to serve as a proof of concept, a demonstration that humans could maintain a functioning biosphere inside a sealed enclosure, a necessary precondition, its architects argued, for any serious discussion of long-duration space habitation. The project lasted 2 years as planned. What nobody planned for was everything that happened inside. Within 16 months, the experiment was in serious crisis. Oxygen levels inside the sealed structure had plummeted from the standard 20.9% of Earth's atmosphere to 14.2%, equivalent to breathing at an altitude of approximately 13400 feet, roughly. The elevation of the highest peaks in the Rocky Mountains. At that concentration, the 8 crew members experienced chronic fatigue, so severe it impaired their ability to perform physical labor. Cognitive function deteriorated measurably. Simple tasks required concentrated effort that would have been effortless at sea level. The researchers were not in immediate mortal danger, but they were operating at diminished capacity inside an environment they had designed in a structure, costing more than some small nations' annual infrastructure budgets, surrounded by every sensor and monitoring system their engineering team could install. And nobody had seen it coming. The cause, when finally traced, was a pair of interacting processes that had been overlooked entirely during years of meticulous design and testing. The first was biological. Soil microorganisms, billions of them teeming in the agricultural beds and the rainforest floor, were consuming oxygen through aerobic respiration at rates that dramatically exceeded the photosynthetic output of the plants growing above. To them, the soil had been loaded with organic rich material intended to support vigorous plant growth, and that organic richness was precisely what the bacteria found so appealing. They thrived, they multiplied, they consumed oxygen at a rate the design team had not accurately modeled because the behavior of soil microbial communities at this scale, under these conditions in this configuration, had never been observed before. The second process was chemical. Exposed concrete in the structure's foundation was absorbing atmospheric carbon dioxide through carbonation reactions, a well-understood chemical process in which calcium hydroxide, in curing concrete, reacts with carbon dioxide, form calcium carbonate. This reaction quietly sequestered carbon dioxide molecules that the biosphere's carbon cycle was supposed to recirculate. It was a slow, invisible drain on the atmospheric chemistry, operating continuously and silently beneath the feet of 8 scientists, who had no way of measuring it until the cumulative effect had already become significant. 2 separate processes, one biological, one chemical, neither catastrophic in isolation. Together, they were slowly suffocating the people inside. But oxygen depletion was not the only failure mode manifesting simultaneously. Carbon dioxide fluctuated erratically beyond predicted ranges. Nitrous oxide, a gas that is essentially inert at trace atmospheric concentrations but becomes a potent neurotoxin at elevated levels, accumulated to concentrations that measurably impaired brain function in the crew members, though the cause was not identified until after the experiment concluded. Morning glory vines, freed from the ecological checks that controlled their spread in natural environments, overran sections of the agricultural zone and choked out food crops with a vigor that horticulturalists had not anticipated. 19 of 25 vertebrate species introduced into the system went extinct. All pollinating insect species died, eliminating natural reproduction for every plant species dependent on insect pollination. Cockroach and ant populations, liberated from the predators that had perished, exploded into infestations that the crew battled throughout the mission without ever achieving control. The agricultural zone yielded insufficient calories. Crew members lost significant body weight. They were hungry, cognitively impaired by low oxygen and accumulated nitrous oxide, physically weakened and increasingly at odds with one another. Interpersonal conflicts escalated until the group fractured into 2 factions that communicated primarily through intermediaries for extended periods. Emergency oxygen injections from outside were required to maintain safe concentrations for human habitation. The material seal had been broken. The core premise of the experiment, complete closure, had failed. Biosphere 2 was not a poorly designed experiment. It was an extraordinarily well-funded, meticulously planned attempt by some of the most qualified ecologists and systems engineers of its era. Its failure was not a failure of effort or expertise. It was a failure of complexity. The system contained more interacting processes than its designers could model, predict, or control, and that surplus of complexity expressed itself as cascading instability the moment the doors closed and the consequences of every design decision became irreversible. This principle carries implications for generation ship concepts that cannot be argued away. Closed ecosystems are not merely difficult to sustain, they are inherently unstable at small scales. Natural ecosystems on Earth achieve their apparent stability through mechanisms that no buildable vessel could replicate. Planetary ecosystems buffer local disruptions through geographic scale. A forest fire in one region is absorbed by unaffected biomes thousands of miles away. They benefit from atmospheric and oceanic circulation driven by solar energy input across an entire hemisphere, distributing heat, moisture, and chemical compounds globally. They maintain biodiversity reservoirs containing millions of species, ensuring that if one functional group declines, others can partially compensate. They operate nutrient cycles that involve geological processes, volcanic outgassing, tectonic subduction, continental weathering, unfolding across timescales of millions of years. These are not engineering features. They are planetary-scale phenomena that emerge from the interaction of an entire world's worth of mass energy and biological diversity. A generation ship possesses none of these buffering mechanisms. Its ecosystem is confined to a volume measured in thousands or tens of thousands of cubic meters, rather than the roughly 1 trillion cubic kilometers of Earth's biosphere. Its species inventory is limited to whatever organisms were deliberately introduced, plus whatever microorganisms hitchhiked aboard undetected. Its nutrient cycles must operate in perfect closure because there is no geology beneath the floor, no ocean to absorb chemical imbalances, no atmosphere stretching across a hemisphere to dilute a local surplus. And this artificial balance must be maintained not for the 2 years that defeated Biosphere 2, but for centuries, a time span roughly 100 times longer than the experiment that already exceeded the ability of its designers to anticipate. The atmospheric balance problem alone illustrates the razor-thin margins involved. Human respiration consumes oxygen and produces carbon dioxide. Plant photosynthesis reverses this exchange. In principle, the two processes balance. In practice, the balance depends on dozens of interacting variables: light intensity and duration, plant health, leaf area, index, soil microbial activity, temperature, humidity, nutrient availability, and carbon dioxide concentration itself, which acts as both a metabolic product and a photosynthetic substrate. A shift in any single variable propagates through the system, altering the equilibrium in ways that may develop slowly enough to evade detection until the deviation has become difficult to correct. Oxygen concentration must remain within a band of approximately 16 to 23% for safe human habitation. Below 16%, physical performance deteriorates sharply, as the Biosphere 2 crew discovered at 14. Below 12%, unconsciousness occurs within minutes. Above 25%, the flammability of virtually every organic material aboard increases dramatically, transforming a routine electrical spark into a potential conflagration capable of consuming the agricultural zone before suppression systems could respond. Carbon dioxide must remain below approximately 1% for long-term health. Above that threshold, chronic exposure causes headaches, impaired cognitive performance, and cardiovascular stress that compounds with every other physiological burden the crew already bears. Above 5%, acute toxicity becomes lethal within hours. Maintaining these concentrations within tolerance across centuries requires either mechanical atmospheric processing, which draws on the same degradation-prone machinery already discussed in detail, or biological regulation through a carefully managed plant community, which introduces the instabilities demonstrated by Biosphere 2. The realistic answer is that a generation ship would need both simultaneously, with mechanical systems serving as the primary buffer and biological systems providing supplemental cycling. But this means the atmospheric management system inherits the vulnerabilities of both approaches at once: the material wear and component failure of engineered systems, combined with the ecological fragility and unpredictability of living onus. Water recycling presents a parallel challenge with its own compounding difficulties. A population of 1,000 humans requires approximately 2 to 3 cubic meters of potable water per day for drinking, food preparation, and hygiene. Agricultural systems require substantially more, perhaps 10 to 50 times the direct human consumption, depending on crop selection and cultivation method. The total water budget for a generation ship might circulate 100 to 200 cubic meters per day through various purification and recycling loops. The International Space Station's water recovery system reclaims approximately 93% of wastewater, including processed urine, humidity condensate, and hygiene water. Advanced systems under development target recovery rates approaching 98%. But even 98% recovery means 2% loss per cycle. Over thousands of cycles spanning years and decades, these small losses accumulate into significant deficits. Unless every molecule of water vapor, every drop of moisture absorbed by a surface, every trace amount sequestered in microbial biomass is eventually recovered. More insidiously trace contaminants accumulate in recycled water streams with each pass through the system, pharmaceutical metabolites, endocrine-disrupting compounds, heavy metal ions leaching from aging plumbing materials, chemical byproducts of sterilization processes. On the International Space Station, activated carbon filters and ion exchange resins remove these contaminants, but the filter media are consumable, requiring periodic replacement from Earth-delivered supplies. A generation ship must either carry sufficient filter media for the entire voyage, an enormous mass penalty, or develop the ability to regenerate spent materials from onboard resources. This is a chemical engineering challenge that has not been demonstrated at the required scale, let alone across the required duration. Food production demands controlled environment agriculture, operating without interruption for the full mission duration. Hydroponic and aeroponic systems in which plants grow in nutrient solutions or misted environments, rather than soil, offer higher yields per unit volume than traditional farming and allow precise control of nutrient delivery. But they introduce a dense web of mechanical dependencies: pumps circulating nutrient solutions, sensors monitoring chemical composition, lighting arrays providing photosynthetically active radiation across the correct spectrum, climate control maintaining optimal temperature and humidity within tight tolerances, sterilization systems preventing pathogen accumulation in recirculating fluid. Each dependency is a failure pathway. A pump failure interrupts nutrient delivery. A lighting array degradation reduces photosynthetic output below the threshold needed to maintain atmospheric oxygen balance. A sensor drift leads to incorrect nutrient concentrations, producing deficiency symptoms in crops before the error is identified. A sterilization failure permits pathogen colonization of the root zone, potentially destroying an entire growing cycle before the infection can be contained. The genetic dimension of agricultural sustainability introduces a subtler but equally serious long-term risk. Crop populations maintained in isolation gradually lose genetic variation through two mechanisms operating simultaneously. The first is genetic drift, the random fluctuation of gene frequencies that occurs in any finite population regardless of selection pressure, simply because each generation draws a limited sample from the previous one. Rare genetic variants disappear by chance alone. The second is artificial selection pressure. Crops grown generation after generation under identical controlled conditions are gradually selected for performance under those specific conditions, losing the genetic versatility that allowed their ancestors to cope with variation. After 10 or 20 generations of isolated cultivation spanning perhaps 200 to 400 years, depending on the crop's generation time, a variety that began the voyage with robust resilience may have become finely tuned to current conditions, but brittle against any perturbation of them. Reduced genetic diversity diminishes resistance to novel pathogens, and the pathogens share the ship. This is the dimension of the problem that deserves the most careful attention because it involves an asymmetry that no amount of careful crop management can neutralize. Plant generation times span months to perhaps a year. Microbial generation times span minutes to hours. A bacterial population cycles through roughly 10,000 to 50,000 generations in a single human year. In the time it takes a wheat crop to complete 20 generations, the microbial community in the root zone has completed perhaps 10 million. Natural selection operates with enormous efficiency across that many generations. Mutations that improve a pathogen's ability to overcome the crop's existing resistance mechanisms are tested, selected, amplified, and spread through the microbial community on timescales that make human agricultural response essentially impossible without access to external genetic resources. On Earth, plant breeders respond to emerging pathogen strains by crossing cultivated varieties with wild relatives carrying novel resistance genes. This is the foundation of modern disease resistance, breeding the system that has kept global agriculture one step ahead of rapidly evolving fungal, bacterial, and viral pathogens for the past century. It works because wild relatives exist in natural habitats around the world, carrying allelic diversity accumulated over millions of years of co-evolution with precisely the pathogens threatening the cultivated varieties. When a new virulent strain of wheat rust emerges in East Africa, breeders at international agricultural research centers can find a resistant wild grass on a Central Asian hillside, cross it with commercial varieties, and develop resistant cultivars within a few growing seasons. A generation ship has no wild relatives. It has no natural habitats. It has no hillsides. When a pathogen evolves the ability to overcome the resistance mechanisms present in the ship's crop population and over centuries in a closed environment with rapid microbial evolution, this is not a possibility, but a near certainty. The crew cannot breed a resistant replacement. They must find a chemical or biological control method using only the resources aboard to accept the permanent loss of that crop from their diet, or watch their caloric foundation collapse while attempting to scale up alternative food sources that were never designed to bear the full nutritional burden. The loss of even a single major staple crop would trigger consequences that cascade far beyond the dinner table. Caloric insufficiency reduces physical work capacity. Reduced work capacity means fewer labor hours available for maintenance tasks that keep every other system functioning. Fewer maintenance hours means faster degradation of mechanical systems. Faster mechanical degradation means more failures in life support. More life support failures means more stress on the biological systems compensating for them. More stress on biological systems means greater instability in the atmospheric and water cycles. Greater atmospheric instability means reduced crop yields, completing a feedback loop that tightens with every revolution. Below the roots and above the crop canopy, invisible to every sensor the ship carries, a community of microorganisms is making decisions, not consciously, but through the relentless pressure of natural selection that will determine whether the atmosphere remains breathable, whether the water remains drinkable, and whether the soil remains productive. Those decisions are being made on timescales of minutes, in populations numbering in the trillions across millions of generations, in an enclosed system with no external inputs to buffer their collective drift. Soil on Earth contains roughly 10,000 distinct bacterial species per gram, drawn from a global pool of microbial diversity, so vast that its total number of species has not yet been catalogued. When a particular strain declines in one field, others migrate in from surrounding environments. The wind, the water, the roots of adjacent plants maintaining functional redundancy across the microbial community. The system replenishes itself continuously from a reservoir that is, for practical purposes, inexhaustible. Aboard a generation ship, the microbial community loaded at departure is the only microbial community that will ever exist. There is no surrounding environment. There is no reservoir. The community that arrives at the destination, if the destination is ever reached, will bear almost no resemblance to the community that departed Earth. It will have been reshaped by millions of generations of selection pressure, operating entirely within a closed system, optimizing for whatever the enclosed environment rewards, with no guarantee that what the environment rewards happens to align with what human survival requires. Managing these invisible ecosystems across centuries demands microbiological expertise of a kind currently practiced by specialists at research universities and agricultural extension services, people who spent years acquiring the training, to monitor microbial community composition using DNA. Sequencing equipment interpret the results against a background of deep ecological knowledge and intervene effectively when communities drift toward unfavorable configurations. Each of these capabilities faces the same degradation curves as every other technical capacity aboard. The DNA sequencing equipment ages, the reagent supplies deplete, the analytical software runs on processors that are failing and cannot be replaced. The specialists who understood the system retire and age and die, passing an incomplete version of their knowledge to students who will pass an even less complete version to theirs. What biosphere, too, demonstrated in 16 months under ideal conditions on Earth, with emergency intervention available at any moment, operated by some of the most qualified ecological scientists of its generation, was that a closed ecosystem's behavior cannot be fully predicted from first. Principles cannot be perfectly controlled through engineering and will express surprises that no design review can anticipate. Every surprise it expresses must be managed using only what is aboard. Every surprise that cannot be managed becomes a permanent feature of the new equilibrium, whether or not that equilibrium is compatible with human survival. The lesson is not that closed ecosystems are impossible. They are not. Small, simple ones have been maintained for years. The lesson is that complexity is the enemy of closure. Every additional species, every additional chemical cycle, every additional interaction pathway between biological and mechanical systems adds another dimension of potential surprise. A generation ship capable of feeding and sustaining a population of several hundred to several thousand people across centuries would contain an ecosystem of extraordinary complexity, and that complexity would be navigating through time entirely alone without the planetary safety net that buffers every ecosystem on Earth against the consequences of its own unpredictability. The air will drift, the water will accumulate things it should not, the crops will lose something they were born with, and the microorganisms will keep evolving indifferent to the mission statement, indifferent to the destination, indifferent to everything except the immediate selective pressure of the enclosed world they inhabit. But even if every mechanical system holds, and even if the ecosystem maintains its precarious balance, the people inside the vessel carry a vulnerability that is not written in steel or soil. It is written in the four-letter code of their own DNA. And cosmic radiation is already editing that code one high-energy particle at a time in every germ cell of every person aboard. The consequences accumulate not across years but across generations. And the mathematics of what that accumulation means for a small, closed inbreeding population is among the most disturbing calculations in the entire analysis. Every second of every day aboard a generation ship, something invisible is passing through the bodies of everyone aboard, not through the walls. Through the walls, through the shielding, through the clothing, through the skin, through the soft tissue, through the bone marrow, and through the nucleus of every dividing cell in every organ of every person living their entire life inside that vessel. Galactic cosmic rays, particles accelerated to fractions of light speed by supernova shockwaves distributed across the galaxy stream through the interstellar medium in every direction simultaneously, and no practical thickness of shielding can stop the most energetic among them. The biological consequences of this exposure unfold on two distinct timescales. The first is the lifetime of the individual. The second is the lifetime of the population across generations. Both are serious. The second is potentially civilization ending. Begin with the individual. The radiation environment in interstellar space, beyond the protective influence of any star's magnetic field and heliosphere, delivers an unshielded whole-body dose of approximately 300 to 400 millisieverts per all year. This figure comes from instruments aboard spacecraft operating beyond Earth's magnetosphere, confirmed by the radiation assessment detector aboard NASA's Curiosity rover during its cruise phase to Mars, which measured cumulative doses broadly consistent with these estimates for deep space transit. For comparison, the average annual background radiation dose on Earth's surface is approximately 3 millisieverts per year. The interstellar environment delivers roughly 100 times that. Shielding reduces this exposure but cannot eliminate it. Hydrogen-rich materials, polyethylene water liquid hydrogen, if carried as fuel, are the most effective shielding substances for cosmic rays, because hydrogen's single proton produces fewer dangerous secondary particles when struck by incoming ions compared to heavier elements. A shielding configuration equivalent to approximately 20 grams per square centimeter of polyethylene, roughly the hydrogen content of about 20 centimeters of water surrounding the inhabited areas, reduces the dose from lower energy particles substantially. But the highest energy galactic cosmic rays, the heavy ions carrying enormous kinetic energy designated HZE particles in radiation biology for high charge and energy, are so penetrating that no practicable shielding thickness stops to them. Worse, when very high energy particles strike heavy shielding materials like iron or lead, they initiate cascades of secondary particles through nuclear spallation reactions. These secondaries can actually increase the dose to occupants behind heavy shielding for the most energetic incoming particles. This counterintuitive phenomenon means that for the extreme end of the cosmic ray energy spectrum, adding more dense shielding material can make the interior radiation environment worse rather than better. Even under the most optimistic shielding scenarios, achievable without impractical mass additions, the residual annual dose to inhabitants likely falls in the range of 100 to 200 millisieverts per year. Over a 70-year human lifespan, this accumulates to 7 to 14 sieverts of absorbed dose. For reference, a cumulative dose of 1 sievert is associated with approximately a 5% increase in lifetime cancer mortality risk, based on the linear no-threshold model derived from extensive epidemiological studies of atomic bomb survivors in Hiroshima and Nagasaki. At 7 sieverts accumulated over a lifetime, the increase in cancer mortality risk exceeds 30%. At 14 sieverts, it approaches levels that significantly compress life expectancy and degrade quality of life across the final decades. Every person born aboard the vessel faces this exposure from the first moment of their existence, not from adulthood, from conception. The developing fetus is among the most radiation-sensitive biological systems known, particularly during the periods of rapid cell division and organ differentiation that characterize the first and second trimesters. Epidemiological studies of populations exposed to elevated radiation during development, including children of atomic bomb survivors and populations in regions of naturally elevated background radiation, document measurably increased rates of intellectual impairment, developmental abnormalities, and childhood cancers at doses considerably lower than those projected for generation ship inhabitants. Children conceived and gestated in the interstellar radiation environment would face these elevated risks before they were old enough to comprehend their situation. Fertility itself is vulnerable in ways that compound over time within a small population. Both oocytes and spermatogonia, the precursor cells from which eggs and sperm develop, show radiation sensitivity at doses well below those that cause acute radiation sickness. Chronic exposure at the levels expected aboard even a well-shielded interstellar vessel could reduce fertility rates measurably across the population, shrinking the effective reproductive pool with each generation. Reduced fertility in a small, closed population is not merely a demographic inconvenience. It is a direct attack on the genetic future of the mission. This is where the analysis transitions from the health of individuals to something far more consequential: the genetic health of the population across the generations the mission requires. Every cosmic ray that damages a germ cell's DNA, not the somatic cells of the body that will die with the individual, but the reproductive cells that will carry genetic information forward to the next generation, has some probability of creating a heritable mutation. Most such mutations are neutral, producing no detectable effect on the organism that inherits them. A substantial fraction are deleterious, reducing biological fitness in ways ranging from subtle metabolic inefficiencies to severe developmental disorders. A very small fraction are beneficial, marginally improving some function in a particular environment, and a very small fraction are lethal, killing the embryo before development completes. In a large population numbering in the millions or billions, this continuous influx of new mutations reaches an equilibrium. Deleterious mutations are diluted by the enormous genetic diversity of the breeding population and gradually purged by natural selection over many generations. The mutation load, the cumulative burden of harmful alleles carried by the population, stabilizes at a level that reduces average fitness slightly but does not threaten population viability. This equilibrium has been maintained in large natural populations for millions of years. In a small closed population of several hundred to several thousand individuals, the equilibrium breaks down. New mutations introduced by radiation cannot be diluted by outbreeding with unrelated individuals from outside the group because there is no outside. Deleterious alleles accumulate faster than selection can remove them, a phenomenon population geneticists call mutational meltdown, first described theoretically by Michael Lynch and colleagues in the early 1990s, and subsequently confirmed in experimental populations of organisms ranging from viruses to small invertebrates. Each generation carries a slightly higher burden of harmful mutations than the one before. Average fitness declines incrementally. Fertility drops marginally. infant mortality rises marginally. Developmental abnormalities become marginally more frequent. The population does not collapse suddenly. It spirals slowly, generation by generation, toward genetic impoverishment, maintaining its numbers for a time through cultural encouragement of reproduction, while the underlying biological quality of each successive generation quietly deteriorates. The minimum viable population question, how many individuals must the founding crew include to prevent this spiral, has generated serious scientific debate and a range of quantitative estimates that carry direct relevance to generation ship planning. A widely cited study published in 2014 by Cameron Smith at Portland State University calculated that under idealized conditions, perfectly random mating, no mate choice preferences, no population bottlenecks, and no elevated mutation rate beyond normal background levels, a founding population of approximately 98 individuals could maintain acceptable genetic diversity over 10 generations. This figure entered popular science writing and has been cited extensively in discussions of generation ship demographics. But the assumptions underlying that calculation deserve scrutiny because they describe a human society that has never existed and almost certainly never will. Humans do not mate randomly. They exhibit strong preferences based on proximity, cultural affiliation, perceived physical attractiveness, social status, and a phenomenon called genetic similarity, preference that may reflect unconscious kin recognition. These preferences systematically reduce the effective breeding population size below the census population size, the actual number of individuals alive, sometimes dramatically. When more realistic social constraints are incorporated into population genetic models, the required founding population rises to estimates ranging from 500 to approximately 5,000 individuals, depending on assumptions about mating patterns, generation time, acceptable inbreeding, coefficients, and whether any active genetic management program is imposed on the population. Even at the higher end of this range, the population remains small enough that genetic drift, the random fluctuation of allele frequencies that is an inescapable consequence of finite population size, operates as a powerful evolutionary ethos. Rare alleles disappear through chance alone, regardless of their functional importance. An allele present in only 2 or 3 individuals in the founding population might be critical for resistance to a pathogen not yet encountered, or for optimal function of a metabolic pathway under conditions not yet experienced. If those 2 or 3 individuals happen not to reproduce, or happen to reproduce with partners who do not carry the allele forward, it is gone permanently. No subsequent generation can recover what drift has eliminated. Inbreeding depression, the reduction in biological fitness that occurs when closely related individuals reproduce, expressing deleterious recessive alleles that would normally be masked by functional copies from unrelated parents' compounds. The drift problem in any finite closed population. The coefficient of inbreeding, which measures the probability that 2 alleles at any genetic locus are identical by descent from a common ancestor, rises with every generation in a closed breeding population. The rate of increase depends on population size and mating structure, but the direction is invariant, always upward. A founding population of 1,000 individuals with imperfect mating management would show measurably elevated inbreeding coefficients within 5 to 10 generations, roughly 125 to 250 years. Within 20 generations, 500 years, the accumulated inbreeding would begin expressing consequences documented in both human populations experiencing founder effects and in conservation breeding programs for endangered species. Reduced fertility, elevated susceptibility to infectious disease, increased rates of congenital abnormalities, and decreased average lifespan. The agricultural parallel to this genetic tragedy is vivid enough to make the abstract mathematics visceral. In the autumn of 1845, a water mold called Phytophthora infestans arrived in Ireland and encountered the Irish potato crop. The Irish agricultural system at that time depended overwhelmingly on a single variety, the Irish lumper, which had been selected and propagated for its exceptional yield in Irish soil conditions. The lumper was everywhere. It had displaced virtually every other variety from Irish fields because nothing else fed as many people per acre. That genetic uniformity was also a catastrophic vulnerability. The lumper possessed no resistance to Phytophthora infestans. Every potato plant in the country carried the same susceptibility. The pathogen did not need to overcome diverse defense mechanisms across a genetically varied population. It needed to overcome one mechanism, replicated in every field across the entire island simultaneously. Within 2 years, the potato crop had failed catastrophically. Approximately 1 million people died of starvation and related disease. Another million emigrated. The population of Ireland fell by roughly 25% in 5 years and continued declining for decades. Now, consider the generation ship's situation in light of this history. The Irish potato monoculture was a single variety maintained in isolation for perhaps a few decades before disaster struck. A generation ship's crop populations would be maintained in isolation for centuries, subject to far more severe genetic drift-facing pathogens that would be evolving continuously within the same enclosed environment. The genetic diversity of the ship's agricultural stock at mission year 500 would be considerably less than the Irish lumper's already dangerously narrow genetic base, and the ship would have no alternative source of calories to fall back on, no grain reserves in government warehouses, no relief shipments from overseas, no wild plants in uncultivated fields that the population could harvest in desperation. The loss of a staple crop in deep interstellar space is not an agricultural emergency. It is an existential one. Cryopreserved genetic material, frozen embryos, cryopreserved oocytes and sperm, representing the genetic diversity of a much larger founding population than the active crew, could theoretically provide a reserve that partially mitigates both the agricultural and human genetic risks. This strategy is used in conservation biology programs for critically endangered species, where frozen gametes from deceased individuals can be thawed years or decades later to introduce genetic diversity into a living population. Applied to a generation ship, it would allow the crew to periodically introduce genetic material from the frozen reserve into the active breeding population, refreshing allelic diversity and resetting the inbreeding coefficient toward lower values. The strategy is genuinely promising in principle. It would extend the genetic viability window significantly beyond what could be achieved without it. But it introduces dependencies that carry their own failure probabilities across the same extreme timescales. Cryogenic storage systems maintaining samples at temperatures below -130 degrees Celsius must function without interruption for the full mission duration. A warming event lasting even a few hours could denature proteins and destroy cell membrane integrity throughout the stored samples, eliminating the genetic reserve in a single incident. The cryogenic system thus becomes a failure point of extraordinary consequence, a single component whose malfunction would eliminate an irreplaceable resource that cannot be recreated from any other onboard material. The reproductive technologies required to utilize the frozen reserve in vitro, fertilization, embryo, cryopreservation, and thawing gestational surrogacy protocols demand specialized medical equipment, precise chemical reagents, and practitioners with deep technical training. Each of these dependencies follows the same degradation curves as every other technical capacity aboard. Equipment ages, reagents expire, practitioners die, and must train successors, with each transmission of knowledge losing some fidelity. After 10 or 15 generations of knowledge transfer, the practitioners managing the cryogenic genetic reserve may retain a general understanding of the protocol without the granular technical mastery needed to execute it successfully when it matters most. And there is a human dimension to this strategy that purely technical analyses tend to omit. The social acceptance of assisted reproduction as a routine institutionally managed practice across centuries of isolated habitation is not guaranteed. It requires cultural norms that actively value genetic diversity management governance structures, capable of making and enforcing decisions about breeding that individuals might resist as intrusive, and a continuous social consensus that the technical complexity and personal intimacy of the protocol are legitimate subjects of collective oversight. In a population experiencing the psychological pressures of permanent confinement, resource scarcity, and multi-generational uncertainty, maintaining that consensus across dozens of generations is not a given. Social upheaval, ideological shift, or simple institutional decay could render the genetic reserve functionally inaccessible long before it is physically depleted. The compounding of these genetic, agricultural, and reproductive risks over time produces a picture that the individual elements alone do not fully convey. Radiation raises the mutation rate. A higher mutation rate accelerates mutational meltdown in a small population. A small population is more vulnerable to genetic drift. Genetic drift reduces allelic diversity. Reduced allelic diversity increases susceptibility to pathogens. Increased pathogen susceptibility threatens crop yields. Threatened crop yields reduce caloric intake. Reduced caloric intake impairs fertility. Impaired fertility further shrinks the effective breeding population. A smaller effective breeding population experiences faster drift and more rapid inbreeding coefficient increase. The spiral tightens with every revolution driven by forces operating simultaneously at the atomic level in irradiated DNA, at the population level in allele frequency distributions, at the ecological level in pathogen crop coevolution, and at the social level in the cultural systems governing reproduction and resource allocation. None of these forces is hypothetical. All of them are grounded in well-established science, radiation, biology, population genetics, epidemiology, agricultural history. None of them spontaneously reverses. All of them trend in the same direction across extended timescales. And all of them operate on a population that is simultaneously managing a deteriorating mechanical infrastructure, a drifting closed ecosystem, and the full weight of an existential psychological burden that no human society has ever faced. What no genome can carry forward, however, is the knowledge of how to keep the vessel functioning. The genetic health of the population determines whether the people aboard can survive biologically, but biological survival is insufficient. The people who survive must also know how to maintain the systems that sustain them, and knowledge, it turns out, is as mortal as any organism. More mortal in some ways, because it can vanish not through death, but through forgetting. Through the slow dissolution of the institutional structures that once held it, passed it forward, and gave it meaning. History has recorded this dissolution before. It has recorded what happens when the chain of transmission breaks, when the people who understood something essential cease to exist and leave behind only documents that subsequent generations can read but can no longer fully comprehend. The consequences were catastrophic on a planetary civilization with billions of people and unlimited geographic space to recover in. Aboard a generation ship, the consequences of a broken transmission chain are not recoverable. They are simply the new reality, permanent, irreversible, and measured in the growing gap between what the vessel requires and what its inhabitants still know how to provide. In the year 27 BC, Roman engineers completed a harbor structure at Caesarea Maritima on the coast of what is now Israel. They mixed volcanic ash from the Pozzuoli region near Naples with seawater and lime, poured the resulting material into wooden forms submerged beneath the Mediterranean, and allowed it to cure in direct contact with salt water. The resulting concrete hardened into a substance of extraordinary durability. 2,050 years later, marine archaeologists examining the submerged remnants of that harbor found the concrete not merely intact, but in some respects stronger than the day it was poured. To a consequence of a mineral reaction between the volcanic ash and seawater that had continued slowly for 2 millennia, progressively reinforcing the material's microstructure. Modern Portland cement concrete, the material from which virtually every significant structure on Earth has been built for the past century and a half, begins to degrade within decades of exposure to seawater. Roman concrete improves. The formula was lost, not stolen, not deliberately concealed, not destroyed in a single catastrophic event. It was simply no longer taught, because the social and institutional structures that had once transmitted the knowledge from master to apprentice across generations of Roman construction practice had dissolved, along with the empire that sustained them. The texts describing the process survived in libraries. Vitruvius wrote about it in De Architectura. The documents were readable. But reading a description of a process and possessing the tacit expertise required to execute it are separated by a gap that no amount of careful scholarship can fully bridge. It was not until modern materials scientists applied X-ray diffraction and electron microscopy to surviving samples that the chemical mechanism was finally understood, not recovered from the tradition that had once embodied it, but reconstructed from scratch using analytical tools that did not exist until the 21st century. Roman concrete is not an isolated case. It is an illustration of a principle that runs through the entire history of human technical knowledge, that knowledge is not a static archive. It is a living transmission. It exists not in documents, but in the continuous chain of understanding, passing from one human nervous system to another through teaching, demonstration, apprenticeship, and shared practice. When that chain breaks, the knowledge does not go into hibernation awaiting rediscovery. It dies. What remains in the documents is a shadow sufficient to confirm that the knowledge once existed, insufficient to reconstruct it without independent reinvention. Greek fire, the incendiary weapon that allowed the Byzantine navy to dominate the eastern Mediterranean for centuries, burning on the surface of water and clinging to enemy hulls with a ferocity that no contemporary technology could match, was lost when the specialized military units responsible for its manufacture were disbanded as the empire contracted. The exact composition remains disputed by historians and chemists today. The texts describe its effects in vivid detail. They do not preserve its formula with sufficient precision for modern chemists to reconstruct it with confidence. The knowledge died with the people who held it, and the documents they left behind are a monument to their expertise rather than a transmission of it. The great library of the House of Wisdom in Baghdad, established under the Abbasid Caliphate in the 8th century, represented the most concentrated repository of mathematical, astronomical, medical, and philosophical knowledge in the medieval world. When the Mongol siege of 1258 destroyed the city, the caliph was executed, the population was massacred, and the library's contents were dispersed, burned, or thrown into the Tigris River, which reportedly ran black with ink for days. The scholarship that survived did so in fragments scattered across institutions that lacked the interpretive community, the living network of scholars who had understood, contextualized, debated, and extended the knowledge that had once given to it meaning. Subsequent generations could read the surviving texts. They could not always comprehend them without the tradition that had once surrounded them. Branches of scholarship that had been advancing for centuries stagnated for generations, not because the texts were gone, but because the living knowledge was. These examples carry a specific implication for generation ships that deserves to be stated with precision. A generation ship could carry a complete digital archive of every technical manual engineering reference, scientific paper, maintenance procedure, and operational handbook ever written for every system aboard. This archive would fit comfortably on a storage medium, massing a few kilograms. Its existence would provide genuine value, a reference library of extraordinary depth available to any crew member who knew how to search it. But documentation alone does not constitute competence. The gap between reading a manual and possessing the expertise the manual describes is not a gap of information. It is a gap of experience, judgment, and the accumulated tacit knowledge that accretes in a skilled practitioner through years of working with the actual systems under actual conditions. Consider what it means to maintain a fission reactor coolant pump. The manual describes the pump's specifications, the permitted operating ranges for temperature and pressure, the procedures for disassembly and reassembly, the torque values for fasteners, the clearances required between rotating and stationary components. This information is essential. Without it, maintenance is impossible. But an experienced reactor technician brings something to the pump that the manual cannot provide. The knowledge of what a healthy pump sounds like at various operating speeds, the specific vibration signature that precedes bearing failure by approximately 40 hours, the way coolant flow rate responds to early-stage impeller erosion before any instrument alarm, triggers the subtle change in the pump's thermal behavior during startup that indicates a developing seal leak long before fluid loss is detectable. This knowledge is not written anywhere. It lives in the nervous system of the practitioner, built through thousands of hours of direct interaction with the actual machinery, under the guidance of more experienced practitioners who possess the same embodied knowledge. This tacit knowledge, the expertise that lives in hands and instincts rather than in text, transfers only through direct mentorship. An apprentice learns by watching, by assisting, by gradually assuming responsibility under supervision, by making small mistakes in contexts where they can be caught and corrected, by absorbing the judgment of a master practitioner until the judgment becomes their own. The process is slow, deeply personal, and irreplaceable. No database, however comprehensive, can substitute for it. No training simulation, however sophisticated, can fully replicate the texture of real experience with real systems under real consequences. A generation ship requires the continuous production of trained engineers, medical practitioners, agricultural scientists, life support technicians, systems analysts, and specialists in every domain critical to the vessel's function. Each generation must transmit sufficient technical knowledge, both formal and tacit, to its successors to maintain the ship's complex infrastructure at an adequate level of competence. This transmission requires functional educational institutions, comprehensive and current documentation, practical training facilities with access to actual systems rather than just simulations, a surplus of experienced practitioners willing and able to dedicate time to teaching, and a cultural value system that prizes technical competence highly enough to allocate the resources necessary for its development and preservation. A single generation that fails to adequately train its successors creates a knowledge gap that may prove irreversible. The failure need not be total or sudden. A partial failure. A cohort that understands the procedures but not the principles, that can execute routine maintenance but cannot diagnose novel failure modes, that knows what to do in expected situations but lacks the deep understanding needed to improvise when the unexpected occurs, represents a degradation of capability that will not be apparent until the unexpected situation actually arrives. By that point, the knowledge needed to address it is no longer aboard. The mechanisms through which a generation can fail to adequately transmit its knowledge are numerous and historically well documented. Social upheaval diverts resources and attention from education. An epidemic that kills disproportionately among senior practitioners, the teachers and masters rather than the young, eliminates institutional memory faster than any training program can rebuild it. Cultural shifts devalue technical work relative to other social pursuits, reducing the number of talented young people who choose engineering and science over status-generating alternatives. Governance failures defund or dismantle educational institutions during periods of resource scarcity, producing a generation of practitioners whose training was incomplete. Ideological transformations reframe technical expertise as the legacy of a discredited prior regime, deliberately breaking continuity with accumulated knowledge that is inseparable from the cultural context that produced it. Every one of these mechanisms has operated in human civilizations throughout recorded history, producing the losses already described. Every one of them would be available to operate aboard a generation ship in a confined environment where social pressures are amplified by the absence of any escape valve, where resource scarcity is structural rather than cyclical, and where the consequences of knowledge loss are not recoverable from any external source. The normalization of deviance provides a framework for understanding how these failures develop without triggering the alarm responses that might prevent them. Sociologist Diane Vaughan coined this phrase in her analysis of the organizational failures that produced the Space Shuttle Challenger disaster, the process by which small deviations from established standards, each individually manageable and rationalized as acceptable, gradually accumulate into a systemic departure from safe practice that is invisible to the people operating within it, because each step away from the standard was taken incrementally and normalized before the next step began. Aboard a generation ship operating in its third or fourth century, the engineers maintaining the atmospheric processing system have never worked with equipment operating at original specifications. Their entire professional formation has occurred in the context of a ship already operating at degraded capacity. The tolerances they accept as normal, the performance metrics they consider adequate, the failure modes they regard as manageable routine, rather than alarming departures. All of these are calibrated against a baseline that is already significantly below the baseline their great-grandparents inherited. They are competent within their context. Their context is a context their great-grandparents would have found alarming. The generation living on a ship operating at 60% of its original capability has no direct memory of the ship at 100%. Their professional judgment, their sense of what is acceptable and what is concerning their threshold for intervention, all of these are calibrated to 60% as the normal condition. This is not negligence. It is the inevitable consequence of formation within a degraded environment. The problem cannot be solved by training people to remember that things were once better. They cannot remember what they never experienced. It can only be addressed by maintaining documentary records of original specifications with sufficient institutional authority that subsequent generations accept those specifications as binding rather than aspirational, and by maintaining the measurement capabilities needed to determine how far current performance departs from those specifications. Both of these requirements face the same degradation pressures as every other technical capability aboard. The psychological weight borne by the middle generations, those born centuries after departure and centuries before arrival, represents a dimension of the generation ship problem that engineering analysis tends to treat as peripheral, but that may prove as decisive as any mechanical failure mode. Consider the existential position of a person born aboard the vessel in its 350th year of flight, with perhaps 400 years remaining before arrival. This individual did not choose the mission. The choice was made by ancestors separated by 14 or 15 generations, people who are as remote in time as the founders of medieval European kingdoms are from inhabitants of the 21st century. The person born in year 350 will live their entire life inside the vessel. They will never see a natural sky. They will never feel wind that has traveled more than the length of a corridor. They will never experience the sensation of standing on ground that extends beyond the walls of a structure, of looking toward a horizon that recedes as you walk toward it. Every landscape they will ever know is a ceiling. Every weather they will ever experience is a climate control setting. Every sunrise they will ever see is a lighting schedule executing on automated timers. Their entire existence is instrumental. They exist to maintain the vessel, to reproduce, to train successors, and to pass the mission forward to children who will be in exactly the same position, instrumental, confined, and serving a purpose whose fulfillment lies beyond the lifetimes in both directions. The founding generation at least carried the memory of Earth, the anchor of a chosen mission, and the psychological grounding of having once known an open horizon. The arrival generation carries the anticipation of a destination, the galvanizing prospect of stepping onto a new world and witnessing the mission's purpose fulfilled. The middle generations carry neither anchor nor anticipation. They inhabit a perpetual present defined entirely by maintenance and reproduction in service of a goal that belongs to the dead and the unborn simultaneously. Research on isolated confined human groups consistently documents elevated rates of depression, anxiety, interpersonal hostility, and social withdrawal under conditions of prolonged confinement that are far less extreme than those a generation ship would impose. Studies of Antarctic overwintering crews, submarine deployments, and long-duration spaceflight missions reveal that these psychological effects manifest within months and intensify with duration. The record for continuous human spaceflight, Valery Polyakov's 437 days aboard the Mir space station, provides valuable data on individual psychological adaptation across roughly 14 months of confinement. It says nothing about multi-generational psychological sustainability in a sealed environment from which there is no return under any circumstances. Every civilization that has endured across centuries has offered its members forms of meaning rooted in the present, in community, in spiritual practice, in connection to landscape and season, and the living world that surrounds them, in the sense that their individual actions participate in something larger than themselves that is happening now, not in the lives of ancestors they never met or descendants they will never know. A generation ship offers metal corridors, recycled atmosphere, a maintenance schedule, and a mission statement authored by the dead on behalf of the unborn. Whether human psychology can sustain purposeful collective functioning under those conditions for century after century is a question no experiment has approached and no theory can confidently answer. Social stratification, political conflict, ideological schism, and resource disputes have characterized every confined human community in recorded history. They emerge under conditions of perceived injustice, resource scarcity, power concentration, and ideological divergence, all of which a generation ship would experience at multiple points during a voyage of centuries. Mutinies, governance, collapses, and civil conflicts are not anomalies in the human record. They are recurring patterns, expressing themselves across cultures and time periods with a regularity that suggests they reflect something fundamental about human social dynamics under pressure, rather than the failures of particular individuals or institutions. A governance system that functions admirably in the 1st century may be experienced as oppressive tyranny by the 5th, when the original social contract has been reinterpreted across 15 generations by people who never agreed to it. A technical hierarchy that maintains vital expertise at its apex in the 2nd century may calcify into a hereditary caste system by the 6th, with access to critical knowledge restricted by birth rather than distributed by demonstrated competence. A resource allocation system that operates fairly when reserves are adequate may become a mechanism of brutal inequality when scarcity intensifies, generating the resentments that fuel the social ruptures that destroy educational institutions and interrupt the knowledge transmission chains that keep everyone alive. The biological, mechanical, ecological, and social failure modes of a generation ship are not independent threads that might be addressed separately. They are woven together so completely that pulling any one thread tightens the others. A social crisis that disrupts education, reduces technical competence, which accelerates mechanical degradation, which stresses life support, which threatens the ecosystem, which creates food scarcity, which fuels further social crisis. The spiral has no natural flaw. It simply tightens until something breaks in a way that cannot be repaired. What remains is to ask the question that all of this qualitative analysis demands to be made quantitative. Not how might these failure modes interact, we have described that in detail, but what the mathematics of their interaction means in aggregate. What probability does a generation ship actually have of surviving its voyage intact, not in the language of narrative or analogy, but in the cold language of compound probability that treats a generation ship not as a story but as a system, and asks what systems of this complexity operating under these conditions across these timescales actually do? The answer is arithmetic. And arithmetic does not negotiate. Imagine a chain composed of 1,000 links. Each link is forged from excellent steel by a skilled blacksmith working at the height of their craft. Each individual link has been tested and found to have a 99.9% probability of holding under load in any given year. You would trust your life to any single link without hesitation. The material is sound. The workmanship is beyond reproach. You examine each link individually and find nothing to concern you. Now hang a heavy weight from the entire chain and ask a different question. Not whether any individual link is reliable, but whether all 1,000 links will hold simultaneously year after year for a century. In the first year, the probability that every single link survives is 0.999 raised to the power of 1,000. The result is approximately 36.8%, not 99.9%. Not even close to 99.9%. Roughly 1 chance in 3 that the chain survives its first year intact. By the second year, assuming each link's annual failure, probability remains constant. The probability that every link has survived both years drops to approximately 13.5%. By year 5, it falls below 1%. By year 10, the probability that all 1,000 links have survived without a single failure is approximately 0.005%, a number so small it is functionally indistinguishable from impossibility. This is the mathematics of compound failure probability. It is not pessimism, it is not engineering conservatism expressed as dramatic rhetoric. It is arithmetic, and arithmetic does not respond to optimism or determination or the extraordinary ingenuity of human engineers. It simply calculates. The critical insight embedded in that calculation is this: it does not matter how reliable individual components are in isolation. What matters is how many components must function simultaneously and for how long. Systems composed of many individually reliable elements become collectively fragile over extended timescales, and the relationship between the number of components, the duration of operation, and the resulting survival probability is not linear. It is exponential. Doubling the number of critical components does not halve the survival probability. It squares it. Doubling the mission duration does not halve the survival probability. It raises the already diminished probability to a further power. The mathematics bends away from survival with gathering steepness as either variable increases. A generation ship is not a chain of 1,000 links. It is a web of tens of thousands of interdependent subsystems, components, biological processes, and social structures, each subject to its own degradation curve, each influencing the failure probability of every other component it interacts with. The compound failure mathematics governing such a system does not merely bend toward difficulty. Over sufficient time scales, it converges on prohibition. To make this concrete, rather than abstract, consider a deliberately simplified model. Suppose a generation ship depends on 10 major subsystem categories for mission, survival, structural integrity, power, generation, atmospheric, processing, water recycling, food production, thermal regulation, radiation shielding, maintenance and manufacturing capability, propulsion and navigation, and medical capacity. Each subsystem encompasses hundreds of individual components and multiple redundant pathways. But for modeling purposes, assign each subsystem a single probability of adequate function across any given decade. This probability incorporates all internal redundancies, repair capabilities, and component replacement from onboard stocks. It represents the net result of everything working in the subsystem's favor against everything working against it. Set that per decade reliability at 95%. This is deliberately generous. It assumes that within any 10-year period, each of these 10 subsystems has only a 5% chance of degrading below the performance threshold needed for mission survival, despite all the material fatigue, radiation damage, consumable depletion, ecological drift, and human factors continuously operating against it. 95% reliability per decade sounds almost reassuringly high. It would be extraordinary performance for any real complex system operating without external resupply. The probability that all 10 subsystems function adequately across a single decade is 0.95 raised to the power of 10, approximately 59.9%, a roughly 40% chance of at least one critical subsystem failing within the first 10 years, even under these generous assumptions. Over 2 decades, the probability of uninterrupted all-system function drops to approximately 35.8%, over 50 years to approximately 7.7%, over 100 years to roughly 0.6%. Over 500 years, the survival probability requires scientific notation and rounds to zero for any practical engineering assessment. These numbers are not precise predictions. They are schematic illustrations built on simplified assumptions. The actual survival probability of any specific generation ship would depend on engineering details, redundancy architectures, crew capabilities, and initial resource inventories that cannot be specified in the abstract. But the qualitative conclusion they illustrate is robust and does not depend sensitively on the specific numbers chosen. Even with generous assumptions about individual subsystem reliability, the compound probability of simultaneous multi-system survival declines rapidly with mission duration. Changing the per-decade reliability from 95% to 98% shifts the survival curves rightward along the time axis, but does not change their fundamental shape. The exponential decline continues. It begins from a more favorable position. It still converges on zero. The assumption of independence between subsystem failures makes the model optimistic rather than pessimistic, because in reality, subsystem failures are not independent. They are strongly correlated. This correlation is the defining characteristic of complex interconnected systems under stress, and it means that failures cluster rather than distributing evenly across time. When something goes wrong, multiple things tend to go wrong simultaneously, because the same underlying cause, a power fluctuation, a structural compromise, a sudden change in atmospheric composition, affects multiple dependent systems at once. Reliability engineers quantify this clustering through common cause failure analysis. In nuclear power plant, safety assessments, common cause failures, events that simultaneously disable multiple redundant safety systems through a shared vulnerability, dominate the risk profile at long time scales. A fire in a cable routing area can disable both the primary and backup control systems for a reactor cooldown pump in the same instant. A seismic event can damage multiple independent cooling water intakes simultaneously. The nuclear industry manages these risks through physical separation of redundant systems. Diverse design approaches that ensure redundant systems fail through different mechanisms and defense-in-depth strategies that multiply barriers between initiating events and catastrophic outcomes. A generation ship would employ similar strategies, but the duration of exposure to common cause failure initiators exceeds nuclear plant design lifetimes by roughly an order of magnitude for near-star missions at 5% of light speed, and by 2 orders of magnitude for missions to more distant targets at 1% of light speed. Common cause failure modes that would never manifest within a 40-year reactor operating lifetime become near certainties across 400 or 4,000 years of continuous operation. The strategies that successfully contain common cause failure risk over decades are not strategies that have been validated over centuries. They have never needed to be. Nothing humanity has built has ever needed them to be. The repair rate versus failure rate dynamic introduces a temporal dimension to the compound failure problem that static probability models cannot capture. Early in the mission, when spare parts inventories are full, technicians are recently trained. At the peak of their expertise, diagnostic equipment is freshly calibrated and manufacturing systems are operational and fully supplied. The repair rate comfortably exceeds the failure rate. When a component fails, it is quickly identified, accurately diagnosed, and efficiently replaced. Redundancy consumed by failures is restored through repair. The ship operates with wide safety margins, and the crew has no reason for particular concern. Decades may pass without a serious crisis. But the two curves, failure rate and repair rate, do not remain stationary relative to each other. The failure rate trends upward over time as components accumulate radiation, damage, fatigue cycles, chemical degradation, and micrometeorite erosion. The repair rate trends downward as spare parts inventories deplete, diagnostic equipment drifts out of calibration, manufacturing, precision degrades, and the tacit knowledge supporting effective repair erodes through imperfect generational transmission. Each curve moves in the direction that makes the other more dangerous. At some point during the mission, the two curves cross. Before the crossing, the ship accumulates safety margin. After the crossing, it consumes safety margin. The crossing represents the watershed moment, the point at which the vessel transitions from a state of positive resilience accumulation to negative resilience consumption. This crossing would not be experienced as a dramatic event. There would be no alarm, no threshold indicator, no bright line separating the era of positive margin from the era of negative margin. The maintenance logs would show a gradual increase in the frequency of system anomalies. The spare parts inventories would show a gradual decline in stock levels across multiple categories. Environmental monitoring data would show wider fluctuations around set points, temperatures drifting a few degrees more than they used to before, correction atmospheric composition varying a bit more before the scrubbers bring it back water, purity metrics running slightly lower than specification more frequently. Each individual trend would be slow enough that the crew on duty at any given time could reasonably interpret it as normal operational variation rather than the signature of systemic decline. The generation that inherits a ship operating at 60% of its original redundancy has no direct memory of the ship at 100%. Their professional formation has occurred entirely within the context of the degraded ship. The metrics they regard as normal, the performance they consider adequate, the safety margins they find acceptable, all calibrated to 60% as the baseline. Conditions that would have prompted immediate alarm responses from the founding generation's engineers are normalized as routine by engineers who have never known anything better. This is not incompetence. It is the inevitable epistemology of formation within a degraded context. You cannot be alarmed by the absence of something you have never experienced. Diane Vaughan's normalization of deviance identified in the Space Shuttle Challenger analysis describes exactly this mechanism at the institutional level. The O-ring erosion that destroyed Challenger had been occurring for years before the fatal launch. Engineers had observed it, documented it, raised concerns, and been repeatedly reassured that it fell within acceptable parameters. Each instance of erosion without catastrophic consequence was interpreted as evidence that the system was more tolerant than the specifications suggested, rather than as a warning that the system was approaching a failure mode not fully understood. Each acceptable anomaly lowered the threshold for the next one. The deviation from standard became the new standard, and then it became catastrophic. Aboard a generation ship operating across centuries, the normalization of deviance does not occur once in an institutional context that can be reformed by investigators with access to better information. It occurs continuously in every domain, across every generation, with no external investigators and no possibility of institutional reform informed by outside perspective. The ship that normalized one category of deviation teaches its children to regard that normalized deviation as baseline. Those children normalize a further deviation and teach their children accordingly. The spiral of lowered standards advances through the generations at exactly the pace that prevents any single generation from recognizing how far it has traveled from the starting point. Can this mathematical trajectory be altered through deliberate design choices that change the shape of the curves rather than merely shifting their starting positions? The engineering literature proposes several strategies, each of which offers genuine benefit alongside fundamental limitations that honest analysis must acknowledge. Modular architecture, designing the vessel as a collection of semi-independent habitat modules, each with its own life support, subsystems, power distribution, and atmospheric management, provides the ability to sacrifice failed sections while preserving others. A module whose structural integrity has degraded beyond safe habitation can be depressurized and sealed, removing it from the habitable inventory while preserving the remaining modules from contamination by its failures. This approach genuinely extends viable mission duration. It transforms what would otherwise be a single catastrophic failure into a series of managed retreats, each one accepting a permanent reduction in habitable volume and agricultural capacity in exchange for the continued survival of the remaining population. The extension is real, but it is bounded. A ship that begins with 20 habitat modules and loses one to irreparable degradation every 50 years runs out of habitable modules in 1,000 years. Long before that point, the remaining modules must support the entire population in progressively more crowded conditions, with reduced agricultural capacity, generating food stress, fewer redundant systems, creating greater fragility, and diminished manufacturing resources constraining every repair and adaptation. Modularity buys time. It does not buy eternity. The exponential decline in survival probability continues. It begins from a higher initial value. Advanced artificial intelligence and autonomous maintenance systems represent the technological mitigation most frequently invoked in popular discussions of generation ship feasibility, and at first consideration, the case is compelling. A sufficiently sophisticated AI system monitoring every component aboard, through embedded sensor networks predicting failures before they occur, through pattern recognition in vibration and thermal data, directing robotic repair systems to perform maintenance tasks without human intervention, and retaining perfect institutional knowledge indefinitely in digital form. Such a system would dramatically alter the repair rate curve potentially, maintaining high repair capability regardless of the human factors that would otherwise erode it. The crossover point where failure rates exceed repair rates could be pushed substantially further into the mission. The limitation is not conceptual, it is physical. The processors on which AI systems run are subject to the same radiation-induced displacement damage, the same transistor degradation, the same bit flip accumulation in memory and storage that affects every other electronic system aboard. The sensors providing input to the AI degrade as transducers age, calibration references shift, and measurement precision diminishes. The robotic systems executing maintenance tasks wear and require maintenance of their own drawing from the same depleting spare parts inventories. The AI system is not a separate layer above the physical degradation problem. It is embedded within it, subject to the same failure curves as every other system, with the additional recursive complexity that maintaining the AI requires the same physical infrastructure whose maintenance the AI is supposed to provide. Furthermore, the kind of artificial general intelligence capable of diagnosing novel failure modes, designing repairs, using whatever materials happen to be available after centuries of depletion, and adapting maintenance strategies to the conditions no programmer could have anticipated, does not currently exist. Narrow AI systems capable of monitoring specific parameters and executing predefined responses are well within current technology and would provide genuine value aboard a generation ship. But a vessel 500 years into its voyage presents failure mode combinations, degraded materials, interacting with drifted ecosystem chemistry, interacting with imprecisely machined replacement components, interacting with a population experiencing genetic stress that no training data could anticipate because they have never occurred before. Responding to these genuinely novel situations requires reasoning from physical first principles using degraded information from aging sensors. The gap between narrow AI capability and this requirement is not an engineering gap awaiting the next hardware generation. It is a conceptual gap whose bridging has not yet been demonstrated. Building a mission plan around assumed AI capabilities that have not been demonstrated is identical in character to building a mission plan around assumed fusion propulsion that has not been achieved. Both represent faith in future breakthroughs dressed in the language of engineering confidence. Cryogenic preservation of a substantial fraction of the population offers the most dramatic potential alteration of the biological failure curves. If the majority of passengers could be maintained in suspended animation, the active crew needed to operate the vessel would number in the dozens rather than the thousands. Food production, water recycling, and atmospheric processing demands would fall by factors of 10 to 100. The ecological load on the closed biosphere would shrink to a scale that might remain manageable across centuries. The genetic and social pressures of a large confined population would be correspondingly reduced. The concept is devastating in its practical requirements. Cryogenic preservation of intact human organisms, not tissue samples, not individual organs, but complete living persons, is not a demonstrated technology. Current cryopreservation techniques produce lethal ice crystal formation within cells, despite the use of cryoprotectant agents. Vitrification, the cooling of tissue into a glass-like amorphous state without ice formation, has been achieved for small tissue samples and isolated organs under laboratory conditions. It has never been demonstrated for an intact human body. The gap between vitrifying a kidney and vitrifying a nervous system containing approximately 86 billion neurons with their precise synaptic connectivity intact is not a gap of degree. It is a gap that may approach a difference in kind. Even if vitrification of complete persons were perfected before departure, the cryogenic systems maintaining hundreds or thousands of vitrified bodies at temperatures below -130 degrees Celsius would need to function without interruption for the full mission duration. A power failure, lasting hours, not days, not weeks, but hours, could allow warming to temperatures where devitrification occurs, destroying cell membranes and protein structures throughout every preserved body simultaneously. The cryogenic system thus concentrates risk rather than distributing it. It transforms a vessel with many independent failure modes into a vessel with one failure mode of absolute consequence. A single power interruption, a single cryogenic system malfunction becomes the equivalent of killing every preserved passenger in a single instant. This is not a mitigation of the compound failure problem. It is a different formulation of the same problem with a more catastrophic single-point failure mode substituted for the distributed failure modes it was intended to replace. When these mitigation strategies are incorporated into the compound probability model, modular architecture, extending the survival curve's robust, monitoring systems, improving early failure, detection, cryogenic preservation, reducing biological load, the effect is to shift the survival curves rightward along the time axis. A mission that might have crossed the failure rate exceeds repair rate threshold at 200 years without mitigations might cross it at 350 or 400 years with aggressive application of all available strategies. This is a meaningful difference. For missions targeting the nearest star systems, Alpha Centauri at 5% of light speed, requiring roughly 90 years, or at 3% requiring roughly 145 years, this extended window potentially places the mission within the range of the barely achievable, if not the comfortably achievable. But shifting the curves does not change their shape. The exponential decline in survival probability continues after the shift, descending from a higher starting point, but falling just as steeply. For missions lasting 500 years, the probability landscape darkens substantially, even with all mitigations applied. For missions lasting 1,000 years or more, which are required to reach any star of moderate scientific interest at velocities grounded in known physics, rather than assumed breakthroughs, the compound failure mathematics becomes effectively prohibitive, not impossible. A non-zero probability persists regardless of mission duration because mathematics does not produce absolute zeros in systems of this kind. But the probability that remains at 1,000 years, even under the most generous assumptions, is so small, and the uncertainties surrounding it so large, that no rational engineering assessment could characterize such a mission as having a reasonable expectation of success. It would be an act of hope, not engineering, a commitment to the possibility of an outcome, while acknowledging that the probability of that outcome is vanishingly small, and the stars that most warrant the journey, the systems with Earth-like planets in habitable zones, the worlds that might harbor conditions suitable for human habitation, are not the nearest stars. They are the stars that require the longest voyages. TRAPPIST, one with its 7 rocky planets and 3 habitable zone candidates, sits 39 light-years away. At 1% of light speed, nearly 4,000 years. At 5%, nearly 800. The most scientifically compelling destinations are precisely the destinations where the mathematics is most brutal. The gap between where the survival curves remain meaningful and where the scientifically interesting destinations lie is not a gap that any mitigation strategy currently conceivable can bridge. It is measured in centuries of additional exposure to every failure mode described across this entire analysis. Additional radiation, additional fatigue cycles, additional ecological drift, additional genetic erosion, additional knowledge loss, to additional social stress, and those additional centuries do not merely add to the risk. They compound it because every system aboard becomes more degraded with each year of transit, making every subsequent year of the same transit more dangerous than the year before. The primary barrier to interstellar travel via generation ship is becoming clear. It is not the barrier most people identify. It is not primarily the propulsion challenge, though achieving the velocities needed compresses the problem significantly. It is not primarily the ecological engineering challenge, though that challenge is genuinely formidable. It is not primarily the genetic challenge, or the social challenge, or the manufacturing challenge, though all of these are serious. The primary barrier is time itself. Time is the medium through which entropy operates. Every second of transit is another opportunity for every failure mode to advance. And the relationship between time and mission survival is not linear, not polynomial, but exponential, bending away from viability with a steepness that no engineering achievement can indefinitely resist, because the physics governing the degradation of every system aboard mechanical, biological, ecological, genetic, and social is the same physics that has governed the universe since its first moments, and it has never once been successfully negotiated with. What this means for humanity's ambitions among the stars is the question that demands to be answered honestly without flinching from what the mathematics shows, not what we wish the universe permitted, not what we hope future technology might someday achieve, what the universe as we currently understand it actually allows, and what that means for the extraordinary dream of carrying human life across the void between the stars. We began with a number, 4300000 miles per hour, the fastest any human-built object has ever traveled. A velocity so extraordinary that it transcends every intuitive framework the human nervous system evolved to navigate faster than sound by a factor of 500, faster than a rifle bullet by a factor of more than 300, fast enough to circle the Earth at the equator in less than 4 minutes. We held that number up as a monument to human engineering capability and then watched it dissolve into insignificance against the first calculation it encountered, 6,800 years to the nearest star. A journey so long, it encompasses the entire written record of human civilization end to end twice over and still falls short. That was the beginning of this story. But the distance was never the true antagonist. We have traveled much further since that opening number. We have descended through layer after layer of the actual physics, not the physics of science fiction, not the physics of optimistic projection, but the physics that governs the behavior of metal under cyclical stress of crystal lattices, under radiation bombardment of soil bacteria competing for resources in a sealed enclosure, of DNA accumulating damage in every germ cell of every person born into an environment that a human body was never shaped by evolution to inhabit. We have examined what happens to knowledge when the chain of transmission breaks, what happens to ecosystems when the planetary buffers that sustain them are removed, what happens to genomes when the population carrying them is sealed and isolated for generations beyond count. What we found layer by layer was not a wall of distance, it was a wall of time. The stars are not separated from us primarily by space. They are separated from us by the duration required to cross that space, at any velocity physics permits a material object to achieve. And duration is the domain of entropy. Every second of transit through interstellar space is another second in which every material aboard the vessel advances along its degradation curve. Every biological system drifts further from its initial conditions. Every genome accumulates another increment of radiation-induced mutation. Every knowledge transmission chain introduces another increment of fidelity loss. The degradation is not dramatic. It is quiet and incremental and thermodynamically guaranteed by laws that admit no exceptions, no matter how ingenious the engineering that attempts to work around them. This is the conclusion that the compound failure mathematics delivered without ambiguity. A generation ship mission lasting 1 to 2 centuries targeting Alpha Centauri at velocities of 3 to 5% of light speed under the most optimistic propulsion assumptions sits at the outer boundary of what might be characterized as ambitious but not inconceivable. The engineering challenges are extreme. The biological and social risks are serious. The probability of success under realistic assumptions is not comfortable, but it is not negligible. A civilization with the industrial capacity and scientific maturity to build such a vessel would be undertaking something that the physics does not strictly prohibit, even if it does not warmly permit. For missions lasting 500 years, the probability landscape changes qualitatively. Cumulative material degradation in structural members approaches the limits of any known material's endurance under combined fatigue, radiation embrittlement, and erosion loading. Genetic diversity in a founding population of even several thousand individuals has eroded through 15 to 20 generations of drift and inbreeding in a closed breeding system. The ecological stability of the closed biosphere has been tested by centuries of perturbation without the planetary buffering mechanisms that prevent small imbalances from becoming catastrophic ones. The manufacturing base has consumed a significant fraction of its consumable reserves. The social and institutional structures supporting technical knowledge transmission have been tested across 20 generations of confined habitation under conditions that history gives us no reason to regard as stable across such spans. For missions lasting 1,000 years or more, which are required to reach the scientifically compelling destinations, the systems with potentially habitable worlds, the stars that represent genuine candidates for human settlement rather than merely the nearest targets. The compound failure mathematics converges on a probability so small that honest engineering cannot distinguish it from impossibility with any available analytical tool. Not because any single system is certain to not because human ingenuity is insufficient, but because the number of systems that must simultaneously avoid catastrophic degradation multiplied by the duration of required survival produces a compound probability that the exponential mathematics of reliability theory will not permit to remain meaningful. The barrier is not the propulsion, not the ecology, not the genetics, not the social dynamics. Not any single one of these challenges, each of which is individually formidable, but individually addressable through sufficiently creative engineering. The barrier is all of them simultaneously interacting with each other, compounding each other's effects for a duration measured not in human lifetimes, but in the spans that separate us from the builders of the first cities. Time, always time. And here is what makes this conclusion something other than despair, something that should be held with care rather than dismissed or romanticized, but that contains within it a genuine and important recognition. The generation ship concept is not a failure of human imagination. It is the precise opposite. It is what human imagination produces when it confronts the most humbling physical reality our species has ever encountered and refuses to simply accept defeat. The physics says we cannot cross the void quickly, and the human response, studied seriously by engineers and scientists across decades, documented in peer-reviewed literature, refined through calculation and recalculation, was to ask, can we cross it slowly then? Can we carry everything necessary for survival inside a sealed vessel and endure the crossing through patience and engineering rather than through speed? That question is extraordinary. The willingness to ask it seriously, to work through its implications, without flinching to calculate what it would actually require and confront the answers. Honestly, this is among the most remarkable expressions of the human capacity for long-range thinking in the entire scientific literature. Most species do not think about the stars at all. Most organisms that have ever existed on this planet lived and died without any awareness that the points of light overhead were distant suns, that the distances between them were measured in units that render human experience essentially irrelevant, that the universe extends in every direction to scales that make the entire history of life on Earth a local event of negligible cosmic significance. We are the species that looked up, measured, calculated, and understood all of this. We are the species that looked at the number 6,800 years and asked not how do we accept this limitation, but how do we overcome it? The generation ship is the answer that physics permits when you refuse to stop asking the question. But physics also demands honesty about what that answer costs. The generation ship concept, pursued with full awareness of its implications, asks something of our species that we have never been asked before. It asks us to acknowledge that the universe does not scale to human time, that the distances between stars are not merely large but categorically beyond the scope of any individual human life, any institutional memory, any cultural continuity that history suggests is achievable across centuries of isolation and confinement. It asks us to look at the compound failure mathematics and accept what they show, not as a reason to abandon the aspiration of interstellar travel, but as a precise description of the problem that must be solved before that aspiration can be realized. The solution, if it exists, is not a better generation ship. The solution is velocity, not the marginal velocity improvements achievable through optimization of known propulsion technologies, an additional % or 2 of light speed extracted through more efficient nuclear pulse designs or more precisely shaped propellant distribution. The solution requires a qualitative leap in propulsion capability, one that compresses transit times from centuries to decades, reducing the exposure window through which every failure mode described in this analysis can advance. A mission lasting 20 years faces a compound failure probability landscape that is challenging but navigable. A mission lasting 200 years faces a landscape that is barely survivable under ideal conditions. A mission lasting 2,000 years faces mathematics that no engineering approach currently imaginable can negotiate successfully. Achieving velocities sufficient to compress even the nearest star journeys into spans measured in decades rather than centuries requires propulsion concepts that operate on principles confirmed by physics, but not yet demonstrated in any functioning system. Fusion propulsion, if sustained ignition and net energy gain in a compact throttleable engine are ever achieved, could potentially reach velocities of 5 to 10% of light speed, bringing Alpha Centauri within 15 to 30 years of transit. Beamed propulsion, a powerful laser array in the home solar system, pushing against a reflective sail, could theoretically achieve much higher velocities for appropriately designed payloads, though scaling from the gram-scale probes, envisioned by breakthrough Starshot, to vessels carrying human populations introduces energy requirements that strain the concept. Antimatter propulsion. If antimatter could ever be produced and stored in quantities sufficient for propulsion, rather than the nanograms currently synthesized in particle accelerators, could, in principle, approach 50% of light speed. None of these are engineering prospects in the near term. All of them are directions in which physics points without forbidding. They are problems, not impossibilities. And problems, unlike the second law of thermodynamics, yield to human ingenuity over sufficient time. The generation ship in this light is not the answer to interstellar travel. It is the answer to the question of what to do if nothing better is ever developed, the option of last resort for a species that has run out of alternatives and refuses to accept permanent confinement to a single solar system. As a last resort, it deserves the serious engineering attention it has received. It deserves the honest analysis that reveals its limitations without exaggerating them. It deserves both the admiration and the sobriety that its scale of ambition demands. What it does not deserve is the casual optimism that surrounds it in popular culture. The assumption that a sufficiently advanced civilization could simply build a large enough vessel with sufficiently redundant systems and send a population across the interstellar void with a reasonable expectation of arrival. The physics does not support that assumption. The engineering history of complex systems does not support it. The ecological science of closed biospheres does not support it. The population genetics of small, isolated breeding populations does not support it. The sociological record of human institutional continuity across centuries does not support it. Every discipline that bears on the question arrives at the same conclusion through its own analytical pathway. The barrier is real, it is serious, and it is measured primarily in time rather than in any of the more dramatic parameters that science fiction tends to emphasize. Consider what it means that we know this. That a species which has existed for roughly 300,000 years, which invented writing only 5,000 years ago, which achieved powered flight only 120 years ago, which launched its first satellite only 67 years ago, which sent its first probe beyond the solar system only 47 years ago, that this species has already calculated in precise mathematical detail what it would take to reach another star, identified every failure mode standing between the aspiration and the achievement, quantified the probability distributions of those failure modes across mission durations spanning millennia, and arrived at an honest assessment of where the boundary between the achievable and the effectively impossible currently lies. That is not a story of limitation. That is a story of extraordinary comprehension. The Voyager 1 spacecraft launched in 1977, and currently the most distant human-made object in existence, has traveled approximately 23 billion kilometers from Earth. It is failing. Its power output declines with every passing year as its plutonium-238 fuel decays toward half-life. Its instruments are being shut down one by one to extend the operational life of those that remain. Within a decade or two, it will fall silent entirely, continuing its journey through interstellar space as a mute artifact, humanity's first physical object to enter the space between the stars, carrying a golden record of Earth sounds and images toward a void so vast that it will not approach another star system for approximately 40,000 years. Voyager is too small to carry a person, too slow to arrive anywhere within any meaningful human time frame, too simple to sustain life for even a day. It is by every engineering metric relevant to interstellar colonization utterly inadequate. And it is one of the most profound objects in the history of the universe. Because the species that built it looked at the distance between the stars and decided that sending anything mattered enough to do, because the golden record it carries was compiled by human beings who understood that the probe would travel for tens of thousands of years through empty space, with essentially no probability of ever being found, and chose to include message anyway. Not from optimism, from the same instinct that makes us look up at the night sky and feel something that cannot be fully articulated but will not be silenced. The generation ship sits in the same tradition. It is an attempt to send something more than a probe to send the thing we actually care about, preserving, which is not our data or our artifacts, but our presence, our consciousness, our capacity to experience and understand and care about what we find. The physics that makes this extraordinarily difficult is the same physics that makes the universe worth crossing to understand. The second law of thermodynamics that accumulates entropy in every rivet and seal and genome aboard a generation ship is the same law that drives every star to burn that powers the fusion processes, producing the light under which all life on this planet evolved, that will eventually consume the last star in the last galaxy of a universe, growing cold and dark across timescales that make even interstellar distances seem intimate. We are brief, we are fragile, we are confined for now to a single world orbiting a single star in the outer reaches of a single galaxy among 2 trillion. The odds against our existence were astronomical. The odds against our comprehending our own existence were more astronomical still. And yet here we are, calculating the failure probability of vessels we have not yet built for journeys. We have not yet taken toward destinations. We have not yet reached, driven by something in our nature that the universe did not install for any obvious purpose. And that 4 billion years of evolution on this particular planet happened to produce anyway. The stars are not waiting for us with open arms. They are not waiting for us at all. They are simply burning as they have burned for billions of years before the first cell divided in the first warm, shallow sea on this world, and as they will continue burning for billions of years after everything we have ever built has been unmade by the same entropy that unmakes all ordered things in the fullness of time. We look at them anyway. We calculate the distance, we draw the blueprints, we run the numbers and find the numbers difficult and run them again and find them still difficult and keep working. Not because the universe invites us outward, because something in us cannot conceive of staying. The wall between us and the stars is real. It is measured in centuries of entropy accumulating in metal and DNA and closed ecosystems and fragile social institutions. It is higher than popular imagination acknowledges and more precisely defined than despair suggests. It is not infinite. Physics does not build infinite walls, but crossing it will require more than determination. It will require a quality of engineering, patience, and scientific honesty that we are only beginning to develop the willingness to look at the compound failure mathematics, clearly accept what they show without flinching and work forward. From that honest foundation towards solutions that the universe has not yet forbidden. Somewhere out there, 39 light years from this world, 7 rocky planets orbit a small dim star. 3 of them receive enough warmth to hold liquid water on their surfaces. Whether any of them harbor anything that could be called alive, whether any could support anything that could be called human habitation, remains unknown. What is known is that the light leaving those surfaces right now will reach our telescopes in 39 years. And we will read that light with instruments of increasing sophistication, and we will learn what we can learn from across that distance. And perhaps in some future that is difficult to specify but not impossible to imagine, a generation of engineers will inherit the problem of closing that distance physically, will sit with the compound failure mathematics and the closed ecosystem instabilities and the genetic drift equations and the knowledge transmission challenges, and find in all of that accumulated difficulty not a reason to abandon the aspiration but a precise map of the work that remains to be done. The distance is real. The wall is real. The mathematics is unforgiving. And the light from those 7 worlds is traveling toward us right now, 39 years in transit, crossing the same void that we have spent this entire journey learning to fear and respect and refuse to accept as final. It will arrive, and we will be here reading it, this small and fragile and inexplicably curious species still looking up, still calculating, still reaching towards something the universe has given us no particular reason to expect we will ever touch. A single candle burning in a darkness that stretches farther than light has traveled since the first moment of everything. Still burning,